Imagine stepping into a machine, setting a date, and being whisked away to a different era. The very thought of it sends shivers down our spines, doesn't it? It's like a dream where the boundaries of time dissolve, and we become explorers of the temporal landscape. This is the tantalizing concept of time travel, the ability to move through time, whether to the past or the future, as easily as we travel through space. It's a journey that defies the conventional limits of our existence, opening doors to infinite possibilities. For centuries, time travel has captivated our imaginations, appearing in myths, legends, and stories. From ancient tales of gods and heroes to modern science fiction, the idea of traversing time has been a constant source of fascination. But is it truly possible? Can the fabric of time be manipulated, or is it an immutable constant? Can we escape the confines of the present and journey through the annals of history or into the unknown realms of the future? The allure of time travel lies in its power to offer glimpses of bygone eras, to witness historical events, or to catch a glimpse of what the future holds. The allure of time travel lies in its power to offer glimpses of bygone eras, to witness historical events, or to catch a glimpse of what the future holds. Imagine standing on the deck of the Titanic, or witnessing the signing of the Declaration of Independence, or even seeing what our world might look like 1,000 years from now. However, the notion of time travel also presents us with profound scientific and philosophical questions. What are the rules that govern such journeys? Are there paradoxes that could arise from altering the timeline? What are the implications of altering the past? Could a small change ripple through time, creating unforeseen consequences? Could we, by venturing into the future, unravel the mysteries of our own existence? The future holds secrets that could redefine our understanding of life, the universe, and everything in between. As we embark on this exploration of time travel, we find ourselves at the crossroads of science fiction and scientific possibility. The line between what is imagined and what is possible becomes increasingly blurred. While the idea of time travel has long been a staple of science fiction, recent advancements in physics have hinted at the potential for manipulating time itself. Could the fantastical become reality? Let us delve into the realm of modern physics, where we encounter theories that challenge our understanding of time and its relationship to space. Concepts like wormholes and the bending of space-time offer tantalizing glimpses into the mechanics of time travel. In the vast expanse of the cosmos, time is not a rigid, unchanging constant, but rather a fluid dimension intertwined with space. This dynamic interplay opens up possibilities that were once the domain of pure imagination. This groundbreaking concept, introduced by Albert Einstein in his theory of relativity, forever changed our perception of time. It laid the foundation for a new era of scientific inquiry, one that continues to push the boundaries of what we know about the universe. Albert Einstein, a name synonymous with genius, is often celebrated for his groundbreaking contributions to physics. He revolutionized our understanding of the universe with his theories of relativity, fundamentally altering how we perceive space, time, and gravity. Special Relativity, published in 1905, unveiled the profound connection between space and time, merging them into a single entity, space-time. This theory introduced the idea that the laws of physics are the same for all non-accelerating observers. This four-dimensional fabric of the cosmos, where time is the fourth dimension, forms the very stage upon which the cosmic dance of matter and energy unfolds. It is within this framework that the universe operates, guiding the motion of planets, stars, and galaxies. One of the astonishing consequences of special relativity is time dilation, a phenomenon where time is not absolute but rather relative to the observer's motion. This means that two observers moving relative to each other will experience time differently. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. This effect has been confirmed through numerous experiments, including those involving high-speed particles and precise atomic clocks. This means that time is not a universal metronome ticking at the same rate for everyone, but is instead a personal measure influenced by our motion through space. Each individual's experience of time is unique, shaped by their velocity and gravitational field. Einstein's general relativity, published in 1915, further deepened our understanding of time by revealing its intimate connection to gravity. This theory expanded on special relativity by incorporating acceleration and the influence of gravity on space-time. Gravity, no longer a mysterious force acting at a distance, was reimagined as the curvature of space-time caused by the presence of mass and energy. This curvature dictates the motion of objects, guiding them along the paths we observe. Massive objects like stars and planets warp the fabric of space-time, much like a bowling ball placed on a trampoline creates a dip in the fabric. This analogy helps us visualize how gravity works in the context of general relativity. This warping of space-time is what we perceive as gravity. It is the reason why objects fall towards the Earth and why planets orbit the Sun. Time, intricately interwoven with space, is also affected by this curvature. The stronger the gravitational field, the more pronounced the effect on time. Clocks near massive objects tick slower compared to clocks farther away, a phenomenon known as gravitational time dilation. This effect becomes especially significant near extremely massive objects like black holes. This mind-bending concept has been experimentally verified, confirming that time is not an abstract concept, but a tangible aspect of our universe. Through these experiments, we continue to explore the fascinating relationship between time, space, and gravity. The fabric of space-time, as described by Einstein's theories of relativity, is not a smooth, unyielding sheet, but rather a malleable tapestry that can be warped, stretched, and even torn. This dynamic nature of space-time allows for fascinating possibilities that stretch the boundaries of our imagination. This pliability has given rise to the intriguing concept of wormholes, hypothetical tunnels that connect two distant points in space-time. These wormholes could theoretically act as shortcuts, reducing the travel time between far-flung regions of the universe. Imagine space-time as the surface of an apple. Just as the apple's surface can be traversed in various ways, space-time too can be navigated in multiple dimensions. A worm burrowing through the apple, creating a shortcut between 2 points on the surface, provides an analogy for a wormhole. This shortcut bypasses the longer path along the surface, illustrating how a wormhole could connect distant points in space-time. By traversing the wormhole, the worm bypasses the longer journey across the apple's surface, effectively taking a shortcut through space-time. This concept, while theoretical, opens up exciting possibilities for faster-than-light travel. These theoretical shortcuts, if they exist, could potentially allow for travel between distant regions of the universe faster than the speed of light, a feat forbidden by Einstein's theories within the normal framework of space-time. Such a breakthrough would revolutionize our understanding of the cosmos. Furthermore, some physicists believe that wormholes might not only connect different locations in space, but also different points in time. This raises the tantalizing possibility of time travel, allowing us to journey to the past or future. However, the existence of wormholes remains highly speculative. Despite being mathematically valid solutions to Einstein's equations, we have yet to find any empirical evidence supporting their existence. They arise as valid solutions to Einstein's equations of general relativity, but their formation likely requires exotic matter with negative mass and energy density, something not yet observed in the universe. This exotic matter would be necessary to keep the wormhole stable and open. The immense gravitational forces at play near a wormhole could also potentially cause it to collapse before anything could travel through it. This instability poses a significant challenge to the practical use of wormholes. While wormholes remain firmly in the realm of theoretical physics, they offer a tantalizing glimpse into the possibility of manipulating the fabric of space-time, potentially allowing for shortcuts through the cosmos, and perhaps even journeys through time. The exploration of these concepts continues to inspire scientists and fuel our curiosity about the universe. Time travel in the public imagination, from H.G. Wells to Back to the Future. The concept of time travel has long captured the human imagination, weaving its way through literature, film, and television, becoming a staple of science fiction. From classic novels to blockbuster movies, time travel has served as a narrative device to explore alternate histories, the consequences of altering the past, and the boundless possibilities of the future. H.G. Wells, in his groundbreaking 1895 novel, The Time Machine, introduced readers to a world where time travel was possible, albeit with unforeseen consequences. This seminal work laid the foundation for countless time travel stories that followed, igniting the public's fascination with the concept and its implications. Movies like Back to the Future, The Terminator, and Interstellar have thrilled audiences with their depictions of time travel, each exploring the paradoxes and possibilities that arise from manipulating the flow of time. These films, while rooted in fiction, often incorporate scientific concepts like relativity and wormholes, blurring the lines between fantasy and scientific possibility. Time travel, as depicted in popular culture, often serves as a cautionary tale, highlighting the potential dangers of tampering with the past or the unforeseen consequences of our actions in the future. These stories, while entertaining, also prompt us to reflect on the nature of time, free will, and our place within the grand tapestry of the cosmos. Paradoxes of time. Could you change the past? The concept of time travel, while enthralling, is fraught with logical inconsistencies and paradoxes. One of the most famous is the grandfather paradox, which highlights the potential for causal contradictions when considering time travel to the past. Imagine traveling back in time and accidentally causing the death of your grandfather before he met your grandmother. This action would prevent your own birth, creating a paradox. You wouldn't exist to travel back in time in the first place. This paradox raises questions about the nature of causality, the relationship between cause and effect, and the potential for altering the past. Another paradox, the bootstrap paradox, explores the idea of objects or information existing without a clear origin. Imagine finding a notebook with detailed instructions for building a time machine. You follow the instructions, build the time machine, and travel back in time, leaving the notebook behind for your past self to find. Where did the information in the notebook originate? It has no clear origin, creating a causal loop. These paradoxes, while thought-provoking, highlight the potential for logical inconsistencies when considering time travel to the past. They suggest that our understanding of time, causality, and the nature of reality itself may be incomplete.